Today I plan to cover the so-called negative binomial random variable, which is in section 4.82 of the text. I'm in the Sahara Desert now, as you can see by the way I'm dressed, and it's extremely warm. Okay, so let's get started. So section, this should be in black. So section 4.8.2, which is called the negative binomial random variable. So this section has a lot of calculation in it. I'm going to try to motivate it somewhat differently than the book. So let me do the following. Let's first of all talk about binomial coefficients. So binomial coefficients, again. Let's recall that if I look at m choose k, that's m factorial over k factorial times m minus k factorial by definition. But we can actually do the following. You can absorb the m minus k factorial appearing in the denominator. We can cancel out everything in the m minus k factorial with the first m minus k terms of the m factorial. That leaves the following expression. It's m times m minus 1 times m minus 2 all the way to m minus k plus 1, and everything else cancels after that. And then you're dividing this by k factorial. Okay, so this works when m and k are both greater than or equal to 0, and in fact k should be less than or equal to m. So m greater than or equal to k. Okay, so now suppose that r and k are both greater than or equal to 0, then we make a definition. I'm going to define a negative binomial coefficient. I'm going to choose negative r is now a negative number, or at least a non-positive number. I'm going to define negative r choose k. Here's my definition. So I just copy the formula I just wrote above. I just substitute for m minus r. So we get minus r times minus r minus 1, dot, 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 times minus r minus k plus 1 over k factorial. Now, I can factor out, the numerator has a lot of minus signs in it. So let's factor out, there are k terms, k pairs of parentheses in the numerator. So I can factor out a minus 1 to the k. Ooh, I need more room than that. So we can factor out a minus 1 to the k. And then that if I factor that out, then the r minus r becomes an r, and the minus r minus 1 becomes r plus 1. And then we get all the way up to r plus k minus 1 over k factorial. And then we stare at this and we notice that this is the same thing as minus 1 to the k, r plus k minus 1, choose k. So that's what you get. And also, I should point out, maybe I'll point it out over here. Remember that m choose k is equal to m choose m minus k. So this is also equal to minus 1 to the k, r plus k minus 1, choose r minus 1 if we wanted to write it that way. So let me circle this as a nice equation. Okay, so I'm going to save this slide. So this expression here in the that's boxed by the yellow ink is called a negative binomial coefficient. Okay, and there's something else to say about this that, yeah, so there's another way to write all of this, and that's going to be useful for us. Let's set k equal to n minus r. In other words, n equals k plus r. And let's rewrite this expression in the following way. So it's going to be minus r. Now k is n minus r, so I can get my n minus r on the left side of the equation in the box. And then we have minus 1 to the k, which is n minus r, times r plus k minus 1 is n minus 1. And then we have r minus 1. So this is another way to write it. So I'm going to put that in a box. Okay. So these are both useful ways of expressing the negative binomial coefficient. Okay, so let's put that on hold. I'm going to use this again later. We need this for what follows in the discussion today. My next digression is about so-called binomial series. Okay, so I'm going to clear the screen. Okay, so this is part 2, binomial series. So what's that about? So this is again a digression. This really is not the main topic of today. Some of what I'm going to say now we've seen before. I didn't systematize it. Okay, so so here we go. So let's consider 1 over 1 minus q, or 1 over 1 minus x. We saw that as 1 plus q. Here I'm assuming 0 is less than or equal to q is less than 1, plus q squared, etc. Okay, so that's summation q to the power of k. K goes from 0 to infinity. Okay, so now, so we could call this f of q, and we can compute f prime of q, and that would be the derivative of 1 over 1 minus q, which is 1 over 1 minus q squared. And we did this before. We saw that we got 1 plus 2q plus 3q squared, etc. And this gives me the summation. You could write it like this: k plus 1 times q to the power of k, k going from 0 to infinity. Okay, I'm going to keep going. What about the second derivative? Well, that's going to give me a 2 over 1 minus q cubed. And that's going to be, if you compute what you get, you're going to get 1 times 2 plus 2 times 3 times q plus 3 times 4 times q squared, etc. And that's the sum of what? It's the sum of, if you like, k plus 1 times k plus 2 q to the k. K goes from 0 to infinity. Let's make this a little neater. Let's make this k, put the k plus 1 times k plus 2 over here. I would like to divide both sides by 2, so I'll get 1 over 1 minus q cubed. I will get, it's the sum, k goes from 0 to infinity. Now k plus 1 times k plus 2 over 2, I'm going to absorb the 2 into that. That's k plus 2, choose 2, times q to the power of k. Okay, so we got an expression for that. And the general rule, as I take bigger powers of 1 minus q and take the reciprocal, the general rule is that 1 over 1 minus q to the power of r is equal to the sum, k goes from 0 to infinity, of k plus r minus 1, choose k, times q to the power of k. So, and we can rewrite that as, in terms of the negative binomial coefficient, it turns out this is the same as the sum. K goes from 0 to infinity. Let me look at my notes. Minus 1 to the k times minus r, choose k, q to the k. So this is what I wanted to derive. Okay, so this is the so-called binomial series. This is the binomial series that I was mentioning at the top. Okay. Okay, so I want to define a random variable. It's going to depend on two parameters. It's called the negative binomial random variable. It depends on two numbers. It's going to depend on a number r and a number p, where p will be between 0 and 1. Okay, so here's the definition. So we have independent trials, independent Bernoulli trials, where the probability of success is p. Okay, so let x be the number of trials. X is the, so here's what we do. We play the following game. We don't stop the trials until we have r successes. So it's the number of trials we need to obtain r successes. For example, flip a coin until you get 5 heads. How many times do you have to flip the coin? So now the probability that x is n So the probability of obtaining r successes in n performances of the experiment can be computed in the following way. So if you're going to get r successes in n experiments, that means you have to have obtained r minus 1 successes in n minus 1 experiments. So that gives you, and there are n minus 1, choose r minus 1 ways of getting that. Now you're going to have r successes, so that's p to the r. That's the contribution from the successes, and then you're going to have the remaining are failures. So it's 1 minus p to the n minus r. So this is a probability mass function we'll see in a moment. But any random variable x with this PMF is going to be called a negative binomial random variable. Okay, let's see why this is actually a PMF, a probability mass function. Well, I'm just going to use the fact that p to the r times p to the minus r is equal to 1. And what is that? That's the same thing. If we set q equal to 1 minus p equal to 1 minus q, and use the binomial series, we'll see that this is p to the r times the sum minus 1 to the k, 1 minus p to the k. Oops, I left out a binomial coefficient. I shouldn't do that. So it would be minus r, choose k. I'm using the binomial series on one of the previous slides. Minus 1 to the p to the k. And I can distribute the p to the r through the sum. and I'll get minus 1 to the k. I'll get minus, oops, well, what that is given by, I should say, this is the same thing as summation P of n, because this n minus 1 choose r minus 1, we saw also on a previous slide that that's given by minus 1 to the k minus r choose k, p to the r, 1 minus p to the k. Here k is equal to n minus r. Okay, so 1 is equal to the sum over n of p of n. That's what we needed to see, that this is actually a probability mass function. Okay, so I'm going to do a problem now. Okay, so I got this off the internet, this problem. It's not from the text. Pat Collis is required to sell candy bars to raise money for the 6th grade field trip. There are 30 houses in the neighborhood, and Pat is not supposed to return home until 5 candy bars have been sold. So the child goes door to door, selling candy bars. At each house, there's a 0.6 probability of selling 1 candy bar and a 0.4 probability of selling nothing. So what is the probability in part A of selling the last candy bar at the nth house? So in the solution here is P is going to be given by 0.6. That's success, selling a candy bar. 1 minus P is 0.4. And R is the number of successes we want to be 5. So what is P of n? We're interested in n successes, R successes and n tries. If we go back to the PMF, this would be n minus 1 choose 4. Remember, let me put it back down. P of n is n minus 1 choose r minus 1. P to the r, P to the r, 1 minus P to the n minus r. That's the binomial random variable. And it's the negative binomial random variable. And we can also write this as minus 1 to the n minus r choose n minus r, p to the r, 1 minus p to the n minus r. You could write it in either way. In any case, here r is 5. I'm using the first version of the formula. So we get n minus 1 choose 4. 0.6. 0.6 is given by 6/10 or 3/5. So it's 3/5. Oops. To the power of 5 times 0.4, which is 2/5, to the power of n minus 5. With a little bit of rewriting, this becomes n minus 1 choose 4 times 3 to the 5th power times 2 to the power of n minus 5. That's the numerator of the 2/5 to the power of n minus 5. And then we have a 5 to the 5th and a 5 to the n minus 5th becomes a 5 to the n. So on the denominator is 5 to the nth power. Okay, so that is the solution to part A. Okay, what's the probability that Pat finishes on or before reaching the 8th house in part B? Well, what does it mean to finish on or before reaching the 8th house? That means, so Pat has to at least go to 5 houses because she has to sell 1 candy bar per house. So it would have to be P of 5 plus P of 6 plus P of 7 plus P of 8 is the answer. Okay, and what is that? Well, if we use the formula in the yellow box, that would be, and here I'm using, so n here is going to be 5 or 6 or 7 or 8. We're going to be plugging it in, so we get it's going to be 4 choose 4, and 4 choose 4. 3 to, I'm plugging it into the formula in the blue box actually, 3 to the 5th, 2 to the 0 over 5 to the 5 to the 5th plus 5 choose 4 times 3 to the 5th, 2 to the 1st power over 5 to the 5 to the 6th plus 6 choose 4, 3 to the 5th power, 2 squared over 5 to the 7th plus 7 choose 4, 3 to the 5th power, 2 cubed over 5 to the 8th. And this you can directly compute, and this is approximately equal to 0.59408. So about 60% of the time. Okay, in the last problem, C, the question is, what's the probability Pat exhausts all 30 houses in the neighborhood? And in that case, what we have to do is, the way to solve this is to compute the complementary probability first. So what does it mean to, what is exhausting all 30 houses? That means there are no way you can sell the 5 candy bars no matter what you do. So in other words, we could take the sum n equals 5 to 30 of P of n, and that represents the probability that Pat sells the candy bars. Okay, so what is the complementary probability? 1 minus that. Now, I cannot compute this. There are 25 terms to sum up, and then we have to subtract them from 1. But fortunately, there are calculators online which compute negative binomial probabilities, and the answer is 0.00005658. So it's extremely likely that Pat will exhaust all 30 houses in the neighborhood. Yeah, is what I meant to say. It's extremely unlikely that she's going to have to go to all the houses. So, so that's the answer to part C. Okay. So in the remainder of my lecture today, I want to talk about the expected value of the negative binomial random variable. So I want to get a formula, an expression for the nth moment. So I have to compute the expected value of x to the n. So remember, that's sum of n to the power of k, p of n. So in other words, it's the sum n equals r to infinity. Why is it r to infinity? Because the only way you can get r successes is you have to play the game at least r times. So it's n to the power of k, n minus 1, choose r minus 1, p to the r, 1 minus p to the n minus r. So this expression here is p of n. Okay, so and there's something wrong. This should be expected value of x to the k. Okay, so what do we get when we do this? Well, I'm going to pull out a factor of r over p. We'll see why in a moment. And then it's the sum, n goes from r to infinity. Okay, so I pulled out a factor of p, so it's going to become a p to the r minus 1. The 1 minus p to the n minus r stays the same. And what ends up happening here is with the remaining terms, I want to use an identity, which I'm going to put on the sidebar. There's an identity which I discussed, n times n minus 1 choose r minus 1 is equal to r times n choose r. So in other words, n minus 1 choose r minus 1, dividing both sides by n is r over n times n choose r. We actually derived this way back when, this formula. Okay, so therefore I have an n minus 1 choose r minus 1. So therefore I can substitute an n choose r there. Times an r, but the r I've brought outside. And then n to the k is divided by n to give me an n to the k minus 1. So that's what ends up happening to the formula so far. And so then a little bit of rewriting. I want to set m equal to n plus 1. So what does that give me? I get r over p, the sum, m goes from r plus 1 to infinity of, okay, n to the k minus 1 is m minus 1 to the k minus 1. Then I get m minus 1 choose r. Then I get p to the, oh, I should have put an r plus 1 over here, not an r minus 1, because it's canceling with the p to give you a p to the r that we had on the first line. So that was a mistake. So I get p to the r plus 1 and 1 minus p to the m plus 1 minus r, or m minus r plus 1 if I write it in a slightly different order. Why did I do this? Because this is exactly the same thing as r over p times the expected value of another negative binomial random variable, y minus 1 to the k minus 1, where y is negative binomial, but now not of type r comma p, but r plus 1 comma p. Right, because we have an r plus 1 in the here in the expression. And why do we have a y minus 1? Because there's an m minus 1 here. That's why we have a y minus 1. Okay, so we're going to use this now to actually compute the expected value and the variance. Okay, so let me save the slide and go to a clean slate here. Okay, so what did we get? We got the expected value of x to the n, where x is negative binomial of type r comma p, is given by the expected value r over p times the expected value of y minus 1 to the, it should be x to the k, k minus 1, where y is of type r plus 1 comma p. Okay, so what does that tell us? Let's take k equal to 1. We get the expected value of x is given by r over p times the expected value of y minus 1 to the 0, but 1 minus 1 to the 0 is constant with value 1. Its expected value is 1. So we get that immediately. Okay, so now what does the statement say when k equals 2? The expected value of x squared, or the second moment, is given by r over p times the expected value of y minus 1, which is r over p times the expected value of y minus the number 1, because the expected value of 1 is 1. And this is r over p times, what's the expected value of y? It's y is of type r plus 1p, so you're going to get r plus 1 over p times the expected value of um, uh, so y is of type r plus 1p, so the k then becomes 0 here. So it's r plus 1 over p, and then we have to subtract 1. Okay, so what do you get? So you're going to get that the variance of x is given by the expected value of x squared minus the expected value of x, quantity squared, which is given by what I just achieved for the second moment, minus the expected value of x, which is r over p quantity squared. And now we do some elementary algebra. Let's factor out an r over p, and then we'll get r plus 1 over p minus 1 minus r over p. And then this becomes r over p times 1 over p minus 1. And finally, we can write this as r times 1 minus p over p squared. So the variance of the negative binomial distribution is given by r times 1 minus p divided by p squared. Okay, this is a lot of calculation, I realize, but let's just do an example with all of this. Okay, so let's see how this works in practice. Okay, so let's flip a coin, a fair coin. And how many times, how many flips until let's flip it until we obtain 3 heads, okay? Until 3 heads occur. So what's the expected value of x? What's the variance of x? X is the number of flips. Okay, so here, let's recall what I already computed. I computed the expected value to be r over p, and the variance I computed to be r over p, r times 1 minus p over p squared. So we just have to apply these formulas in this case. So what is r? R is 3. Since the coin is fair, we got p as a half. And so the expected value is r over p, which is 3 divided by 1/2, which is 6. And the variance is going to be given by r, which is 3 times 1 minus p, which is a half, because 1 minus a half is a half, over 1/2 squared. And this is also 6 in this case. So that's the case of a fair coin. What if we do this with a biased coin? the same calculation where P of heads is given by 0.6, or if you like, 3/5. Okay, so what is the expected value in that case? It's R over P, which is, and R again is 3, so it's going to be 3 over 3/5, which is the same as 3 times 5/3, which is 5. So the expected value is 5 now, and the variance is given by, so R, which is 3, times 1 minus P, which is 0.4 or 2/5, because 1 minus 0.6 is 0.4, and then over 3/5 squared. And what do you get here? It looks like you get 2, if you do the cancellations, 2 times 5/3, which is 10/3. So we get 10/3 for the variance and 5 for the expected value. And in both cases, the numbers are smaller, right? The variance is smaller and the expected value is smaller. Well, that's enough for now. And we did a lot of calculation today.